Hello students, good morning. Today I am going to introduce another important result in probability theory, namely Bayes theorem. So it is a statement involving conditional probabilities. Here I have got k events a1, a2, ak, which are disjoint and they form a partition of the sample space, meaning the union of these sets is equal to S. Each of these events has a positive probability and let B be another event with a positive probability. In that case, what I am saying is that probability of AI given B can be expressed as probability of AI into B given AI divided by the summation over all the K events. Now, before we go on to the proof, you might be inquisitive why we are interested in such a complicated expression. So, here B is like an event that has occurred. Suppose there has been an accident. So B is representing the event of that accident, and A1, A2, AK may be the different causes for that accident. So suppose we have a fair idea or an assessment of the chance of these causes and also the chance of accident due to each of these causes. So probability of B given AIs are called the prior probabilities and AI given B is called the posterior probabilities. So Bayes theorem is a method of computing the posterior probabilities in terms of the prior probabilities. We will of course do more, we'll do several examples involving Bayes theorem, but as of now I am just expressing and I'm just writing down the result and discussing the proof, because it is an important result in probability and you can prove it easily from based on whatever you have learned regarding the conditional probabilities. So if I go back to the definition of the conditional probability, please recall that if B is any event with a positive probability, then I can of course condition on the B, and then the conditional probability of AI given B is the ratio. In the numerator we have the probability of B intersection AI, in the denominator I have got B. Now in the numerator, since each AIs also have positive probability, now in the numerator this probability of the intersection can be written as the product of the unconditional probability of AI and now into the conditional probability of B given AI. Okay, so you could split the joint probability in either way. We could also write it as probability of B into AI given B, or I can also write it as probability of AI into probability of B given AI. Only condition is that whatever I am using for conditioning, AI or B, that must have positive probability. And here we are assuming that both PAI and PB all have positive probability, so we can condition by B or condition by AI, there is no problem. So by the chain rule, I am writing the numerator. So this is how I get the numerator. So you see I have got P of AI into probability of B given AI. So the numerator is given. Now only thing that we have to verify is that probability of B is in fact this sum. So in this context, whatever we have learned will become handy. Remember that for any two events A and B between probability of B between 0 and 1, so PA could be written as the sum of PB into probability A given B plus probability of B complement into A given B complement. Now you can think of B and B complement as our A1 and A2. So now instead of 2 I have got B1, B2, Bk, they are disjoint and together they make up the S. So you have to convince yourself that the B event is actually equal to probability of B is actually equal to the sum of the, then the proof is complete. So only one part I am leaving for you. You have to write it this way, that this is equal to sum of, let us B intersection. So insert in intersection. So only this is something you will have to convince yourself. So I am leaving this as an exercise, and then the other part will follow. The second line will follow again from the chain rule. So you see, we have gotten this proof just by the definition of conditional probability, chain rule, and this fact that if A1, A2, AK are disjoint events and together their union is S, then probability of any set can be expressed as the sum of probability of B intersection AI. Okay, let me give you one more hints over here, which will in fact make your job even easier. So we can think of this B as B intersection S. So this should make your job even more simpler. You see why? Because ultimately in B or A or any subset of S, any event here is a subset of S, and so therefore a intersection of S with its own subset is, therefore for any set A or B which is a subset of S, this is true, right? Now S is union of AI, and rest you should be able to figure out. So I am leaving this line where I am writing this B intersection S as the sum of these probabilities is for you as a food for thought, and the rest I think all the steps I have discussed. So this is an important result in probability theory which goes by the name Bayes theorem. And so this I will again we'll continue about this discussion more, and we'll talk about problems, so how this is useful in solving certain problems. Okay, thank you. So just one thing, that here I have said two things, that AI given B remark. So let me write a remark, R-E-M-A-R-K, remark. So this is called posterior probability, P probability. So we are computing the posterior probabilities using the Bayes theorem. So